Hello again, everyone. Welcome to our discussion of section 2.5, where we will talk about transformations of graphs. So what is that? What is transformations of graphs? Well, we have some main functions that we look at in this course as a whole. These are quadratic functions, linear functions, absolute value functions, square root functions, and of course also the cubic functions. So there is a fundamental graph for these functions. That is the graph of each of these functions that runs through the origin, let's say. We'll take that as a standard graph, as the original graph, but then we'll also look at how that original graph can be transformed, in other words, moved or reshaped within the xy plane. How can we take this original graph that has a particular well-known shape and reshape it or redirect it to another location within the xy coordinate system? There's a pattern to that, and we'll look at that in this section. So before we look at the details of that, I want to remind all of you to please read the section 2.5 before you watch this video. It shouldn't be something, say 2 hours or 3 hours assignment. It's something like a half hour or 45 minutes of reading the textbook in that section should be enough. But the point being, skim through the section. Then watch the video and attend the class and take notes on anything that strikes you as important or anything that you might have questions on. Then review your lecture notes and all the problems you saw in the book and all the problems you saw me work on in this video without looking at the solution. In either case, it should be easy for you to cover the solution. In the case of the video, of course, you can always pause the video before you look at the rest of it. In the textbook, you can always cover the solution with a sheet of paper and then work out your own solution, then look at these solutions that you see from the book or from me. That is the way to study mathematics or any quantitative subject. You do not want to just watch somebody solve problems for you. You want to actually solve them on your own with your own thinking. And of course, complete all the homework assignments by the due date. They are mandatory and they should be completed by the due date. And of course, because mathematics is a cumulative subject, you should always spend about half an hour a week to review the older or previous material. Just half an hour a week should suffice to keep things fresh in your mind. Okay, so I want to show you the front page or the first page of the worksheet that I have developed for section 2.5. It looks like this. I've highlighted it. I've highlighted the pieces of it that are important for you to connect as you read this. Okay, so the yellow pieces are critical for you to connect. For example, a function plus a b being some number, is the graph of that original function shifted up. So plus b shifts up, minus b shifts down. If there's subtraction within that function, within the function, within the x itself, not out. See, these numbers b and minus b were outside of the function. But what if it's within the function together with x? Then in that case, shift of the graph happens horizontally, either to the right when we have a minus and positive when we have a shift to the left. So plus means the graph is moved left, horizontally left, minus the graph has been moved right horizontally. Okay, and this is the same for all of these. You should read these, and at first look, you might think, oh, that's too much reading, but this is a summary of maybe 10 pages from your textbook. This is, the first page is a summary of at least 7, 8, 9, maybe 10 pages of your book. So you'd rather read this one page or read 10 pages from the book. You should, as I asked you to skim through the book, that's helpful, but you're skimming through it just to get an idea of what this section is talking about, how are they reasoning about the methodologies and so on. But when you get to reading this worksheet, this will summarize everything you've read that in that section, in these boxes. Okay, so it's well worth your time to read each box, the contents of each box, and make sure that you understand it. But what do all these things say? I mean, aside from reading all these, the contents of these boxes, what do they really say? And I wanted to talk about that by drawing graphs and looking at looking at the equations first, and then we'll go to the computer later to see the effect of all of this in actual graphs. So the fundamental equation for a quadratic function would be this, right? This is the most basic quadratic equation you can have, right? Now, this is an example of a quadratic equation, the most basic example of it. But then the general form always looks like this. F of x equals a times x minus h squared plus k. And these h and k are usually what authors of textbooks use to in the general equation of each of these functions. So I'm using h and k to be consistent with what most books talk about. Okay, so what does this mean in terms of transforming this basic quadratic function? So h is about transforming this function horizontally. If h is some positive value, then that negative stays where it is. So this is the general formula. This is the general form for a quadratic function. H represents some horizontal movement of this original quadratic function. So this is the general form, but if you have a specific form, so this is, let me write this, this is the general form. And this is a specific example, the most basic specific example, in fact. So then you compare this with this, and you ask yourself, what would A must have been to generate this kind of function? A must have been 1, right? There is just one coefficient of x squared term is 1. So this A must have been 1 in this specific example. What about h? What would h have to have been? H would have to have been 0, because if h is 0, then x minus 0 is just x and squared, and a is 1, so 1 times x squared is x squared. Okay, then comparing this with this, what would k have to have been? K would have to have been 0 again, right? Because all of this plus 0 is just itself. So if you remember this, then you can easily look at any specific example and decide whether what each of these must have been. So let me give you another example. So that's the general form. Here is another example. F of x equals minus 3 parentheses x plus 2 squared plus 1. Okay, so you look at this and you compare it with this in your mind. Remembering this, you should remember these general forms. And all you have to remember is one of these. They're all, as you will see me talk about later, they're all exactly the same thing, but the only variation happens for different functions. So for cubic function, instead of squared, you have cubed. For absolute value function, instead of the parentheses and power, you just have absolute value. For the square root function, you just, instead of the parentheses and power, you just have a square root. But the basic structure is the same. So comparing this with that, A is clearly -3. What would then h have to have been? Compare this with this general form of a quadratic function. What would h have to have been for us to end up with x plus 2? H must have been -2, right? Because -2 gives us the +2 that we have here. Okay, what about k? K must have been 1. So what does all this mean? Well, each of these numbers, the -3, the 2, and the 1, as you see them shown in general form in this formula, has a different impact on the graph of the original graph of this quadratic function, which is that. So what does this do? These two, first of all, if it was just +3, it would stretch this graph vertically. It would stretch it. It would stretch it up. And the arms of the quadratic equation would get closer and closer to the y-axis. What about 3? What about the negative? What would the negative do? The negative on the outside, when I say outside, I mean not inside next to x. That would be a different thing. That would be a different impact graphically. We're not talking about negative being here. We're talking about the negative symbol being outside and in front. The impact of this negative in front would be to reflect this graph across the x-axis. Okay, so the 3 would stretch it vertically, and the negative would reflect it across the x-axis. What about this 2 then? Well, the 2 would shift the graph of this horizontally to the left, because as we said earlier, this is the general formula. So if you have +2, then that h must have been -2. So 2 units to the left, because h was -2. And the positive means that h must have been some negative number. How about this 1 then? Well, when k is equal to some positive number, that shifts the graph up these many units. So 1 unit up. Okay, and if this was -2 or -5, it would shift the graph down 2 units or 5 units or however many units that this number would indicate. Okay, do you see the connection? So this is a general form, and these are specific forms. They are specific because you have numbers associated, fixed numbers. But here you have letters, so this is a general form. Okay, so let me talk about more examples of this, and then I'll go to the computer to give you an idea. Okay, so this was a short discussion of transformation of graphs for the quadratic function. Let's choose another function, such as the square root this time. So we have f of x equals square root of x. Okay, So this is the most basic square root function we can have, square root of x. Now this form has a general form. That general means for any square root function. Okay, so the general form for this function, a square root function, is as follows. And as I write this, visually compare the two and see how much they're similar. You see, very, very similar, aren't they? Except the fact that obviously this is a different type of function. This is square root, that's a quadratic function, this is a square root function. But take a look at the similarities, the coefficient a, the k, the h. So what would a, h, and k have, what kind of an impact would they have on the graph of this basic square root function? Well, a, once again, it stretches the graph, the original graph, it stretches it towards or it makes it closer to the y-axis, but that also, I'm talking about these in a very summarized way. Because if you have this a some number greater than 1, then it would stretch this graph towards the y-axis. That's the best way to put it. It would drag the graph, make it closer to the y-axis, or stretch it along the y-axis. Okay? But k would shift the graph up and down, just the same impact that k would have, because this k is outside of the function itself. The main function is the part that involves the independent variable, in this case x. So the main function here is that part, which involves x. Here, the same way, it involves x. Then the k shifts that piece up or down depending on if it's positive or negative. But h, again, you have to be careful here, because suppose we give some specific example. F of x equals 2 square root of x minus 9 plus 6. Right? That's a specific example. This is a general case. This is a general form, because the letters are all free to be any number they want to be, or any number we assign them to be. But here we have a specific example, because those numbers have been assigned. So what kind of an impact how would this shift the fundamental graph of a square root here? Well, this will stretch it towards the y-axis. So however this looks, and we will look at it on the computer, this number 2 will drag it and make it closer to the y-axis, a little bit closer. What about this 9? What impact would that have? Well, compare this whole thing, this whole expression under the radical, with this general form. So what would h have to have been for us to end up with x minus 9? H must have been positive 9, right? It could not have been negative 9, otherwise this minus 9 would make this positive. So h, if this stays negative, that means h must have been a positive value. And if it's a positive value, that indicates horizontal movement to the right. Horizontal movement of what? Horizontal movement of this fundamental function to the right. This 2 stretches the graph of this towards the y-axis. This 9 will move it horizontally to the right. What about this 6? This 6 would move this graph up 6 units. That's why it's so important for you to connect all these three in your mind. There's a significant amount of connection making in your mind and visual connection making in this subject. Okay, so don't look at these in isolation. See them as a whole. How are they related? How are they connected? Think about that. Okay, so another example, we can say minus square root of x plus 7 minus 5. Right? That's another example of a square root function. So how would this function change according to this specific example? Now this function f of x, or let me call it g of x, right? Because that was f of x. So how does g of x transform, and let me also call that g of x. How does this g of x transforms f of x, which was the basic square root function? Well, if you compare, this minus reflects this graph across the x-axis. So it flips it. However this looks, it's going to flip it across the x-axis because of this minus in front. Now, if this minus was inside the function, right next to this x, then that would be flipping the graph of this across the y-axis. So depending on where this minus is, the flipping of the function happens along a different axis. If it's in front, if the negative symbol is in front, the flipping of this function always happens across the x-axis if it's in front and outside of the main function. See, that minus was also in front and outside of the main function, the main quadratic function. So that's what that will do. How about this 7? Compare this general form with this. How would this 7 shift the graph of the basic square root function? Well, see the original form, general form, let me also add, this is the general form. The general form was x minus h, right? But this is x plus 7. So what would h have to have been for us to get plus 7 here? H must have been minus 7, right? Minus 7. So minus 7 means shift of this graph horizontally to the left 7 units. Okay, because of that. So this is why if you see positive, that means horizontal shift is occurring towards the left, because the original general form is x minus h. So if you have plus, that means h was negative. Movement to the left. Now how about k? K is negative 5. What is that supposed to mean? It means that the original graph of the square root of x was moved 5 units up or down? Down, right? Down. Okay, so let's look at another important function, the absolute value function. F of x equals absolute value of x. Okay, so this is the fundamental absolute value function. Let's write down the general form for it. The general form would look like this. And as soon as I write it, compare it with these two, and you'll see immediately how much similar they are. Right? Do you see the sharp similarity? There's a great deal of similarity, right? So the same definitions for moving or transforming the original graph apply here. This A stretches the graph vertically towards the y-axis. So the graph line becomes closer to the y-axis if this a is positive value larger than 1. In fact, well, all of this is explained on that sheet, on this worksheet. On this worksheet that you should read. You should read and understand this worksheet. And again, I've summarized, so this is a summary of several pages from your book. So this is well worth your time. But now I'm explaining, before we go back to the computer and the rest of this section, I want to make sure that you understand how similar they are, these cases are. Okay? So, but how, I mean, I know I'm just briefly explaining that this A stretches the graph of each of these functions towards the y-axis. But there are details to that. If this value of A is something negative for all these three, if it's negative something, it will flip the graph across the x-axis. So the transformation is identical for all these three. The other thing, if this A is some number between 0 and 1, it will flatten the curve. Not completely flat, but it will change the shape so it looks flatter at some juncture. Okay, if this number, A, is between 0 and 1, say 0.2, 0.3, 0.8, it will flatten the graph for all of these. But if it's some number greater than 1, say 5, 3, 2, 8, 10, whatever, then it will stretch it more, or it will sharpen it, not flatten it, but stretch it. It will not shrink it. I mean, your book uses shrinking and stretching. You can think of that flattening as a sort of shrinking. So if this A is between 0 and 1, it will shrink the graph or flatten it. I say flatten because when we go to the computer, that's what you'll see. You'll see the graph kind of flatten. But when the author of your textbook talks about this, he talks about it as shrinkage, not flattening. However best you remember it, use that word, either shrinkage or flattening, if this A is between 0 and 1. If it's greater than 1, it will stretch, or it will stretch it towards the y-axis. If this number is greater than 1, it will stretch it, okay, towards the y-axis. And then so, just like what we've talked before, then let's give a specific example of the absolute value function. Let's say g of x equals minus absolute value of x plus 5 minus 2. So what kind of transformation would this be of the basic absolute value function? Well, this minus in front, again, this minus is in front, not inside, right? The inside, there is no minus. If it's inside, the graph will flip across the y-axis. And I have that here. Right there. As a matter of fact, right in the middle. The graph of negative f of x is the reflection of the graph of f of x across the x-axis. So this minus in front will flip the graph across the x-axis. But if the minus is inside the function, right next to x, the reflection of the graph happens across the y-axis. So all of this is, anything that I'm saying as you watch this video has been captured on this front page. So please take the time to read and understand this. So now that's the effect of that minus. How about this 5? If we have x plus 5 on the inside, what would h must have been? Well, h must have been negative 5, right? Because minus 5 would give us the plus 5 that we have. So if h is negative 5, then the horizontal shift is happening to the right or left. Which one? To the left, right? If h is negative 5, the horizontal shift is to the left. So how about k? K is negative 2. Okay, k shifts the graph up or down. Again, that's on the notes here. Right there. In this case, I've called it B. I guess when I prepared this worksheet, the author of your book says B rather than K. But that's the same thing. B or K, whatever variable, the effect is the same. So plus B shifts the graph up B units. Minus B shifts the graph down B units. So in this case, K, positive K moves it up, minus K moves it down. In this case, it's minus 2, so it moves the graph down 2 units. Let's look at another example. And I have to scroll this up, but you can see the similarity again. This time, let's look at the cubic function, x cubed. So the general form for the cubic function, just like as I write it down, compared with the ones that you see here. I have to scroll this up, so you're not going to see the quadratic term on the screen or quadratic function on the screen, but you have these two to compare to. F of x equals a times x minus h cubed plus k. Right? Compare this with those. They're very, very similar, right? The a in front, the h, the k. So once again, if a it has something negative in front of it, negative 2, negative 6, negative 7, anything, the negative will flip the cubic function across the x-axis. It will flip it the other way. So it's going like that. From it's increasing, it becomes a decreasing function. That's basically what it does. And you'll see it on the computer once I switch. If a, just like before, if a is some number between 0 and 1, 0.3, 0.4, 0.75, something like that, that will stretch the graph of cubic function towards the, or it will flatten it, or I should say shrink it, to use the terminology that your textbook uses. I should say it will shrink it. Or in my own terminology, it will flatten it. And we'll see examples of that on the screen. However, if a is some number greater than 1, say 2, 8, 15, something greater than 1, then that will stretch the graph vertically towards the y-axis. Okay, so that's what that number would do. H, the same impact. If h is negative, the shift is horizontal to the left. If h is positive, the shift is horizontal to the right. K, shift is up if k is positive. Shift is down if k is negative. Here's another specific example of this. Let's see, minus 5 times x plus 3 cubed plus 4. Right? This is once again, these are general forms. And this is a specific example. So a, in this case, is negative 5. The negative part will flip the graph of the cubic function across the x-axis. So because the normal cubic function, it's an increasing function from left to right. It'll increase from left to right. But this minus will make it a decreasing function. So it'll decrease from going from left to right. And you'll see that on the screen, on the computer, when I switch to computer. How about h? What would h have to have been for us to get x plus 3? Well, h must have been minus 3, right? Because if it's minus 3, then minus 3 would give us this plus 3 that we really have. So if h is minus 3, then the horizontal shift is in which direction? To the left or to the right? The horizontal shift is to the left. If you said left, that's absolutely correct. The k in this case is plus 4. So the shift up and down, which way is it? Is it shift up 4 units or shift down 4 units? Shift up 4 units, right? So these are some of the fundamental functions that we will look at in this whole course, and that's why this section looks at transformations of these fundamental functions. We talked about the quadratic function, right? We talked about the square root function. We talked about the absolute value function. And we talked about the cubic function. Okay? So now that we've talked about these, let's go to the computer and look at these effects in more detail using the computer. As I switch to the computer, you'll see your screen blank out in the video. Don't worry about that. It's just because I'm switching from dock camera to the projection screen. Okay, so here we are. So let's graph a whole bunch of these to see how all of this takes shape in different graphs. Okay, we'll look at a whole bunch of graphs. Okay, let's start with the basic square root functions. So we had y equals x squared, right? That's the graph of the basic square root function. But now let's transform it according to what I showed you on the paper, which is g of x equals minus 3 times x plus 2 squared plus 1. So you can see here that the minus in front here has flipped. The flipping that you see, the blue graph, the flipping that you see is the result of this minus in front of the 3, right there, on the left side of your screen, right, the formula. So that minus will flip that original red graph. What about the 3? The 3, compare the arms of the red graph, which belongs to the y equals x squared function, to the arms of the blue graph, which is the transformed version. Notice how much stretched the blue graph arms are. Do you see it? It's the blue graph, the blue curve is much more stretched towards the y-axis. It's stretched, and that's the impact of the 3. And I will change that to some number. Notice that 3 is a number greater than 1, right? So look how much is stretching the graph. In a second, I will change that number 3 to something between 0 and 1, let's say 0.2, and you'll see how that blue graph will change. It'll flatten it out. It will get much more flatter, okay, or shrink. The textbook says shrinkage. Look at this formula. So what h must have been? Do you see what h must have been in this case? H must have been minus 2. It's minus 2, right? Because minus h has given us plus 2. Okay, if it's minus 2, that's why you see this graph move left 2 units horizontally. Move it, you can see the vertex. The vertex used to be at the origin, right? Right there for the red graph. Now it's moved 2 units to the left because h is minus 2. And we know that because we have x plus 2. So h must have been minus 2. And the 1 on the outside, that's the k or b as your book refers to it. So that has moved the vertex 1 unit up. In other words, that vertex really has coordinates minus 2 comma 1. Notice as soon as I type that in, a point or a dot snaps to that vertex, right? We can label it even, minus 2 comma 1. Okay, so shifted horizontally 2 units and shifted up 1 unit. Okay, I hope this is making sense in light of the discussion we had when I was using the paper. Okay, so let's next look at, on paper we looked at the square root function. So once again, let's plot that. The square root function graph looks like this. So that's the fundamental graph. Okay, it looks like that. Now let's transform that using the example. I gave 2 examples. We'll look at both. So g of x equals 2 square root of x minus 9 on the outside plus 6. And let me zoom out so you can see both. So look at, and let me, like that. So look at the impact that this 2 has had on the graph of the purple, or the original one. The square root of x function is the purple one. Now the sec g of x has a 2 in front, so what that did, it stretched this graph closer to the y-axis. If you compare the purple and the black curves with each other, the black curve is closer to the y-axis. I mean, it's leaning more to the left, towards the y-axis. Notice how it's a little bit risen toward the y-axis. Okay? Whereas the purple one is moving away from the y-axis. It's in this curve is a little bit farther, the points on this curve are a little bit farther away from the y-axis. So this 2, the impact of that 2 in front is stretching the graph vertically towards the y-axis. Now what about the h? What is h in this case? The h is positive 9, right? Because the general form is x minus h. So we have x minus 9, which means h must have been positive 9. If it's positive 9, notice how much this original vertex, for the purple one, the original vertex of that was at 0, 0. It has moved how many units to the right? 9 units. And how many units up? 6 units, right? We could have predicted that without looking at the graph. All of that is apparent in the formula minus x minus 9 plus 6. So it moved, this vertex moved from the origin 9 units to the right and 6 units up. As a matter of fact, we can snap to it 9 comma 6 right there. That red dot snapped to it. Let me label it right there, 9 comma 6. Okay. Let's look at what did we look at next? We looked at the absolute value function. So let's do that. Y equals absolute value of x. There's the graph for the fundamental absolute value function right there. A V-shaped graph, right? Then we transform this in which direction? We said minus absolute value of x plus 5 minus 2. Take a look at this. We could have predicted all this behavior without even graphing this, right? How? Well, take a look at this on the left side of your screen. Take a look at this formula. The minus in front of the absolute value predicts that this graph, the blue one, would flip across the x-axis. Did it do that? Absolutely. It's flipped across the x. It's now an up in the green curve, that is, it's an upside down V shape, right? So it flipped. It's flipped down. That's the impact that this minus in front has. How about h? H, in this case, how much is it? What is the value of h in this case? It is minus 5, right? Because look at the inside of the parentheses. It says x plus 5. So h, we know the general form is always x minus h. So if we have x plus 5, then h must have been negative 5. So that negative 5 means that this graph of the original absolute value function has to move 5 units left. And this negative 2 is clearly saying that the shift should be down 2 units. Okay? So that vertex for the blue curve moved 5 units left and 2 units down. In other words, we can snap to that by plotting the point, which would be negative 5, comma, negative 2. Right there, the point snapped to that point. That vertex is the same one at 0, 0. And let me also plot 0, 0, right there. So that black dot became that purple dot after the transformation took place. Okay. What else did we look at? We looked at the cubic function. So y equals x cubed, right? That's what I was telling you, that the cubic function is an increasing function going from left to right, right? So read this graph from left to right. What is it doing? It's going up, right? So it's an increasing function going from left to right. Now let's put in the transformation that we looked at on paper, which was minus 5 times x plus 3 cubed plus 4. Look at that. So look how the graph is flipped, right? It flipped across the x-axis, in fact, and then it was moved up some units and left some units, right? We will look at that. But the flipping across the x-axis happened because of this minus. Look at that. This minus we have in front of the 5. Because of that, this red graph flipped across the x-axis and became the blue one. Now it's a decreasing function, not an increasing function. See, the original cubic function, which is shown in red, is an increasing function. Read it from left to right. But this one, the blue one, after transformation, it's a decreasing function because looking at it from left to right, because of this minus in front. The 5 dragged all those points that you see along the red curve closer to the y-axis. So the graph got stretched towards the y-axis because of that 5. Okay? And then what else that happened? Okay, the h. What is h in this case? We inside the parentheses we have x plus 3, right? So h must have been negative 3. If it's h is negative 3, then the horizontal shift happens 3 units to the left. What about k? K is positive 4, so the vertical shift happens 4 units up. Okay? I should go back. I didn't do this for the previous ones, but I promised you that I would also show you the impact that this a would have on a, in this case is negative 5. I mentioned what impact that a has on the graph if it's between 0 and 1 or if it's some number greater than 1. So you can see that if it's greater than 1, these points get closer to the y-axis. So now let's make that, I'm going to make, you see the original cubic function, which comes first at the top, y equals x cubed. I'm going to give it some coefficient that is between 0 and 1. Let's say to make a point, let's make it 0.1. 0.1 x cubed. That's why I call it flattening of the curve. Look how, I call it flattening. Your textbook calls it shrinkage. But compare that with the red one, which was the original cubic function. That's why I say it's flat. If that number, if that coefficient is between 0 and 1, it'll flatten the curve. We can even go lower. We can go, let me keep that. It's going to make the screen a little bit crowded, but I think maybe it'll be nice to compare all of these together. Let me say y equals 0.02, really much smaller than 1, x cubed. Look at that. That purple graph is really flattening out. Isn't it? Right? Compare the purple with the green and with the red. And compare the coefficients of these functions together. So when the coefficient is between 0 and 1, you're going to see that effect on all these graphs, for the absolute value, for the square root, for the quadratic function, all of them. Okay, and this is for the cubic function. Okay, that's why I wanted to show you that that coefficient is very, very important, and it has that effect on any of these functions that we discussed. As a matter of fact, let's do that for the quadratic function as well, which I remember I didn't do. So I'm going to change all of this to quadratic function so you can see how, look at that, right? If I zoom out, you can maybe see it even, oh no, I didn't mean to zoom in, I meant to zoom out. So the red one is the top or the basic quadratic function. That's what it should look like normally. But if the coefficient is less between 0 and 1, look what happened to the green one, right? That's the one that has coefficient 0.1. And the purple one has coefficient 0.02. Look how much flatter it is. So if the coefficient of any of these functions we discussed is between 0 and 1, it has this effect of flattening the curve, right? Just like that. Now let me put one that has a very high much higher than 1 coefficient, let's say 50. So y equals 50 x squared. Look at that. Look how stretched that graph is, right? It's really stretched. The arms are really stretched, and the whole graph looks really sharp, right? Do you see it? That's the black curve in the middle. So that's why if that coefficient of the quadratic term is higher than 1, it has always that effect. It stretches the arms or the graph towards the y-axis. And that's true for all of the other ones. We can also look at the square root if you want to. So y equals square root of x, right? That's the main square root function with no transformation, right? There's no transformation here. Now let's transform this by saying g of x is equal to, let's give it a coefficient higher than 1. 4 times square root of x. Right? Look at the blue curve. It's stretched because that number 4 is larger than 1. Look how it stretched this graph, the red one, into the blue one, right? It's now, those points are stretched towards the y-axis. This is what I was talking about when we were on the paper explaining this. So let's make that number something between 0 and 1. Right? Let's make it small. So let's make it b of x equals 0.03 square root of x. Oh, I either flattened it out. Do you see it? The green one? Let me zoom in. Well, I don't know if I zoom in, it'll show better. No, that number is too low, so let me increase it so you can have a better idea. I'll make it 0.3. That's better. And let me zoom out. See, the red one is the square root function with no transformation. The blue one is the one that has a, or the coefficient of the square root function, equal to 4. And look how it is stretched towards the y-axis because that number 4 is larger than 1. But look what happens when we enter a coefficient, or a value, which is less between 0 and 1, which generated the green one. Look at the green curve. It's flattened out, didn't it? Or it shrank, as your book calls it. So that is the effect of the a value when it's larger than 1, or if it's between 0 and 1. The square root function is excellent for demonstrating another aspect of what we've been talking about, which is what happens. So I'm going to keep this. The red one is the original the square root function. Let's transform this by using a minus in front. So minus square root of x. Look what happened, the purple one, right? The purple one is the transformed graph. Look at the impact of the minus in front of the square root function. What did it do? It flipped this original red curve across the x-axis to give us the purple one, right? Now, I've been talking about the difference between this minus in front and that minus inside the function, right? So watch what happens as I generate another graph based on the negative sign placed inside the square root. So let's do that. Well, I should actually, let's see. I should probably make that a cube root minus, yeah, this will probably like that. Okay, so Now look at that. So if you put the minus in front, it'll flip the graph across the x-axis, which would be the purple one. If you put the minus inside the square root function, then it'll flip this graph across the y-axis. This is true for all the other functions as well. So let's see. I mean, so we did that for the square root function, right? You can see the effect. I hope you can see the effect of the minus as it's outside and in front, and when it's inside. When it's outside, it flips the graph across the x-axis. When it's inside, it flips the graph across the y-axis. So let's do the same thing, the same examples for the absolute value function. So this is the standard or fundamental absolute value function, right? Like that. Now we're going to transform this by placing a minus in front. So what would be, before I graph this, what would we expect to see? How would this flip across the y-axis or x-axis? Which axis? If the minus is in front, the graph would flip across the x-axis, right there. It flipped across the x-axis, and you can see it exactly what that means. And that's just because of the minus outside of the function and in front of it. What about if we put that minus inside the function, right in front of the x, rather than in front of the function? Well, we expect the graph to flip across the y-axis this time. Let's see it. So what is happening here, and the red one is there, but you don't see it. Why? Because the arms flipped across the y-axis and superimposed over the original absolute value function. Do you see what happened? When we put the negative inside the absolute value function, those red curve arms, the arms of the red curve, absolute value curve, they were flipped across the y-axis, and then they were they superimposed over the red one. But the red one is still there. It's just hidden behind these arms that have been flipped across the y-axis. I mean, we can probably, like that, do that so you can see the red one still there. I just added a 2 to stretch the graph so that you can see the red one. But the reason you couldn't see it before like that is because after the arms were flipped across the y-axis, you couldn't see the ones that were under the red curves that were under that. Okay, but they're there. Okay, so I think this gives you a good idea about how transformation works. So let's go back to our worksheets on the dock camera. Now that we've talked about all of this, so now as you read this front page, you know exactly what it's talking about. And here on the second page here, on the computer and on paper, we've talked about all of this. I'm going to post this on Canvas, but all the examples that you see here, we've gone through similar ones on paper and on the computer. These are just different examples on the same functions. So you have square root function, absolute value function, and the quadratic function here at the bottom. So these are the same functions. And of course the cubic function, which is the one of those 4 different functions we looked at. These are the main functions we look at in this whole course. Okay, so now let us go over these examples. Please, on this page 3, you have 1 through 6, and then we have 7 through 18 example exercises on page 4. So please pause the video. Here, you can pause the video right now. As you're watching this, pause the video before I put down my answers. Answer all these. Answer all these and then watch the rest of the video. Okay, so I'm assuming you've done that. And now you're back. So the first one, if we have the basic quadratic function x squared, then g of x shifts the graph of f of x 9 units right or left. Which one? Left, right? Because h must have been minus 9. The cubic function, given the basic cubic function, g of x shifts the graph of f of x in which way? 4 units. Which way? Left or right? Right. Right, because h must have been positive 4. So it's moving 4 units right. The absolute value function, transformed in this way, shifts the graph 5 units in which direction? 5 units to the left. And 3 units in which direction? Down. Right? I hope these answers agree with what you have written down on your paper. This one, the absolute value function again, and g of x is transforming it. In which way? 3 units. Which way? 3 units which way? Right. Horizontal, right? Horizontally to the right. 2 units. Up. Number 5. We have the square root function, and we want to talk about the transformation of it here in g of x. So 7 units, left or right? H must have been positive 7, right? So 7 units right. Again, square root function. We have square root of x minus 3. So 3 units down. Right? Because this 3 is on the outside. It's not, this 7 is on the inside. So the horizontal shift happens to the right. But this 3 is on the outside of the function. So shift happens up and down, up or down, depending on this value. It's negative, so it's 3 units down. Okay? All right. Oops, it's okay, it's coming back to focus again. The technology is playing tricks on me today. I try, as much as I try not to switch between the dock camera and the computer, because it tends, usually it goes well. It goes well, but sometimes things like that happen and glitches, we start seeing glitches in the transition. I try not to do that, but sometimes, because in this case we're dealing with a lot of graphs, so I wanted to make sure that you fully understood what transformation of graphs are. And the computer does a far, far better job than me of graphing these functions. That's why I used it. But usually I try not to use the combination of these two technologies together as much as possible. But sometimes I can't avoid it. So here, as you can see, we have from 7 to 18. You can see from 7 through 13 now. So now it would be a good idea to pause the video at this moment, write down the answer for all of those on your paper, then come back to the video and see what I wrote. Okay, I'm assuming you've done that and now you're back. So square root is being transformed by this function, and we have 3 units. 3 units in which way? Horizontal, but which way? Right or left? Left, right? Because h must have been -3, which means 3 units left. And 5 units up, right? Again, square root function. Oh, we have a negative in front. What does that do? It reflects the function. If it's in front, it reflects the function across the x-axis, right? So we have reflection across the x-axis. What else do we have? We have 3 units movement up. This one, x squared minus 2. So the graph of x squared is moved 2 units down, right? That was too easy. Number 10, square root function. So what is going on here? How is this transformed using this function? We have 5 units horizontal movement, right? In which direction? Left or right? Right, because h must have been positive 5. So 5 units right, 3 units up. I hope these agree with what you wrote down. So, square root function again, we have 2 units shift, right? In which direction? We know it's horizontal, but left or right? 2 units left, because h must have been -2. The general form is x, it's always x minus h something, right? So h must have been -2, which causes that -2 to give us the +2. So 2 units left and 3 units down. This one is interesting, right? So we have the 3, instead of being placed after the square root, it's placed before it. But the effect is the same. So we have 3 units up movement because of this. But then this minus flips the square root function across the x-axis, and 2 units movement horizontally. In which direction? Left. So we have, I'm going to talk about these in order. So 3 units up, the minus means reflection across the x-axis. And 2 units horizontal shift. In which direction? Right or left? Left, right? H must have been -2. And this one, we have 2 units to the left, right? H must have been -2. 7 units up. This one is really interesting. 4 units up. Reflection across the x-axis because of this minus. and stretching, not shrinking, because of this 3, which is greater than 1, stretching along the vertical axis. And of course, 1 unit to the right, right? And like that. So I was running out of room there. So let me switch here. So here we have 5 units to the 5 units right and 6 units up. Oh, so 16, 17, and 18 are different types of problems. Here they say that given this function, then find another function g of x such that f of x is shifted 8 units to the right. So go ahead, pause the video, answer 16, 17, 18 as best as you can, and then come back to the video. Okay, I'm assuming you've done that. So we're shifting this function 8 units to the right. So let's call it g of x is equal to cube root of, or third root of, x minus 8. Okay, 8 units to the right. This one shifted, the graph of quadratic function shifted 8 units to the left and reflected in the x-axis. So g of x would be x plus 8 units to the left. So x plus 8 squared and also reflected in the x-axis. So with a minus in front. Okay, so minus x plus 8 squared. 18, given f of x equals 1 over x, find the function g of x such that f of x is reflected across the x-axis and shifted up 1 unit. So g of x is equal to reflected across the x-axis, so minus, and this is reflected in the x-axis, reflected across the x-axis, so minus, and shifted up 1 unit. So 1 over x plus 1. Okay. All right, so we've come to the conclusion of another section. I hope these notes and the computer graphs made everything make everything make sense. So I hope that you will ask me any questions you might have. For now, have a nice day. Until next time.